There's such a thing as nuclear hacking. It's what this whole thing is about. Because we're not talking about nuclear technology the way it's done now. We're talking about a completely different approach to nuclear energy than everything we're doing now, and all kinds of improvements. I mean, where did our world of personal computers and all this stuff come from? Did it come from the IBM mainframes? No, it came from dudes having homebrew computer clubs in 1975. We'll look back in the future, and it's meetings and gatherings like this. We'll go, man, that was where it got started. It didn't get started at Westinghouse or Atomic Energy of Canada or GE. None of those guys are going to go build these machines because they're already locked into the solid uranium fuel stuff. They're locked into doing it the way we do it now. And you know what? The way we do it now, it's a really inefficient way to burn stuff because you can't let the fuel get very damaged before you have to take it out. You can't even come close to 100% burn. I mean, not even approaching it. My name's Kirk Sorensen, everybody. I didn't even introduce myself. Don't worry about anything. I live in Huntsville, Alabama. I'm a recovering aerospace engineer, working on becoming a newly minted nuclear engineer. You know what I've noticed? Everybody who's kind of techie just seems to be into energy. You know, it's like you can't avoid getting a kick out of energy. All my NASA buddies were all totally into energy. You know, they'd always want to talk about, let's talk about the energy crisis. I'm like, yeah, we should talk about this rocket. But yeah, you're right, let's talk about the energy crisis. You know, because the thing that caught my eye when I was still in high school was the idea of space solar power satellites. I heard about this a long time ago. And I started reading all these books, and the gist was Gerard O'Neill back in the 70s. Raise your hand if you've read The High Frontier. Right back there, all right. So Gerard O'Neill had a very utopian vision of the future, and I give him full marks for that because we need more people having utopian visions of the future. Well, his idea was we were going to go build these space colonies in space, and it was going to be great. It was going to be like living in a shopping mall in space, you know, and you know, have a little home in the tube, and you said, well, how are you going to pay for this? And the idea was you were going to build these really, really big solar power satellites. These are like a mile across, 10 miles long. So like a Star Destroyer would be small next to one of these things. And this is what the people in the space colony were going to do to pay the bills back home to get Earthlings to keep sending them, I don't know, iPods or whatever it was they were going to want that they couldn't make in their space colony. And it seemed like a great idea because, well, we all knew we needed energy, and solar energy sure seemed great. One of the problems with solar energy is we live on a planet that rotates. Half the day, you don't get the solar energy. Well, up in space, it's always sunny. Build these things, and they're going to shoot the energy back. I mean, this like really affected the way I thought. I want to do this. I want to go make this happen. And so I went to engineering school at Utah State University. I'm a mechanical engineer by training, and I learned all about the important things mechanical engineers learn about, like thermodynamics. And you begin to realize, oh my goodness, you know, nature's actually put certain constraints on what you want to do. You can't just, you know, convert 100% of heat to electricity. That doesn't work, which is that you can't turn all heat into electricity or into work. You only get part of it. On my way out to California to go work at the Skunk Works, I went in a bookstore and I bought this book called The Millennial Project. Now look at this book. Colonizing the Galaxy in 8 Easy Steps. I mean, seriously, that's like crack for an engineer, you know? I mean, I felt the same way about this book that I felt about reading O'Neill's book, The High Frontier. I mean, it was extremely utopian, but a little different. This guy, Marshall Savage, starts out, his first step in his big plan, and it was a big plan. I mean, I got to give him full marks for this. Was he said, we need to build these floating ocean colonies, and we should learn how to live on the open ocean as a preparatory step to learning how to live in space. And I still think he's absolutely right about that. I don't think we're ready to live in space yet. We have not learned how to live in a way where we recycle much more of our, I mean, if you want to live in space, you got to recycle everything. This is a lot easier because you still got the atmosphere to go recycle your air and everything, but you're taking a major step towards being prepared to colonize space. Well, what Savage proposed to power his floating ocean colony, an ocean thermoelectric converter, or OTEC. Anytime you have something that's hot and something that's cold, you can drive an engine between those two things. I mean, they're just the very first principles. OTEC is based on the idea that the water at the surface is warm and the water down deep is cold. The water down deep is very close to freezing, and the water at the surface might be, 80, even 90 degrees. And between those two reservoirs of liquid, you can actually make work or electricity. Now, it's very, very low efficiency. I mean, ideal efficiency for this would be like 4%. Realistic efficiency, probably 1.5 to 2%. I mean, extremely, extremely inefficient. But you have unlimited amounts of cold and you have theoretically unlimited amounts of hot. So between that, he says, well, this would be great. Another really cool thing about it is you bring this cold water up and it spawns all kinds of growth in plant life and animal life, and it's really healthy for the ocean to bring this cold, deep water, because I guess that's where all the nutrients sink. The problem with OTEC is it is very geographically constrained. There's not a lot of places in the world you can do it. The ocean is cold everywhere, but it's only hot in some places. This was a map of this sweet spot of where you'd want to make this work. We don't live really anywhere near this sort of orange bubble here now, do we? In fact, there's almost nobody lives where the orange bubble is. I thought, well, heck, maybe we can make the hot side a little hotter by employing some solar concentrators and juice up this process. Then I had an opportunity after working at the Skunk Works to go to Georgia Tech. And they let me to go to Georgia Tech, not because I had good grades or anything, I really didn't. But my professor found out I'd been on the X-33 and he said, oh, hot dang, you know, come to Georgia Tech and work in our group. I said, well, what are you working on? He goes, we're working on space solar power. I said, oh boy, you know, you had me at space solar power, you know. So I ended up getting a job at Marshall Space Flight Center at NASA. My first job was working in a group that did these really kind of futuristic, far out things. We were looking at nuclear rockets. Now this time I was not particularly excited about nuclear. You know, I thought nuclear, isn't that kind of bad or dirty or yucky or... I just had this sort of vague distaste for nuclear. And we were working on nuclear engines, we were working on really far out stuff. Well, one day, I'm in this buddy of mine's office. He got a book on his shelf, and the book was called Fluid Fuel Reactors. Fluid Fuel Reactor? What the heck is that? I had no idea, never heard of it. And he said, oh yeah, he used to work at Oak Ridge National Labs in Tennessee. And he said, yeah, way back when, they were doing some stuff on this at Oak Ridge. He goes, I just went to the library, and I got this old book. It was written in 1958. And he said, yeah, I've been meaning to look through it. I kind of knew a little bit about it, but not very much. So I took the book home, big old thick book. It was like 1,000 pages. I started trying to read it. I had no idea what the book was talking about. I was just struggling really hard to try to grasp the nuclear concepts in the book. But it was intriguing enough to me, and it seemed really different than the kind of nuclear energy we had now. And they also mentioned in this book a lot about thorium. Thorium. I was like, dude, what the heck is thorium? Okay, it's on the periodic table. It's number 90. It's like 2 spots away from uranium. That's about all I knew. So we'll take it from first principles. Let's talk a little bit about what nuclear fission is. You have fissile nuclei. That means this is a nucleus that if you hit it with a neutron, it's going to fission and split into 2 pieces, 2 fission products. And also significantly, this one neutron is going to spawn the formation of 2 or 3 additional neutrons. Why do we care? Well, here's why we care. Go. Because every kilogram of fissile material will produce as much energy as 13,000 barrels of oil. Nuclear fission is 1,000,000 times more energy dense than a chemical reaction. Civilization has changed over advancements in technology a whole lot more modest than this. When you fission something, it breaks into these 2 pieces, but they're radioactive, and I tried to understand why are they radioactive, and this is a chart that shows the number of protons in matter and the number of neutrons. Now, if the number of protons and the number of neutrons were the same, all of these isotopes would stay on this nice line right here, you see? But they don't do that. At the beginning, it's a roughly equal number of protons and neutrons, but as they get heavier, they definitely get on the very neutron-rich side of things. Okay, so you see these black dots, those are the stable nucleides, and all the other guys are radioactive. The strong nuclear force is holding the nucleus together, and the protons are pushing the nucleus apart. Okay, the protons are all positively charged. They want to rip the thing apart. The neutrons are adding more of that strong nuclear force glue, holding everything together, and they're not adding more of the push it apart stuff. They're not adding more of the repulsive force. So that's why you end up with a lot more neutrons in nuclear matter than in protons. Way down here are uranium and thorium, and they have about 1.5 times as many neutrons as protons. When you bust them in half, the 2 pieces that you get inherit that ratio, but it's the wrong ratio for them. They're over here. They want it to be more like 1 1/4 instead of 1.5. They have too many neutrons. They're neutron rich. you can't dump the neutrons. Nature has a nifty process for fixing this little problem. It's called beta decay. And in beta decay, this is kind of a gross oversimplification, but a neutron essentially turns into a proton and it spits out an electron. When you fission a nucleus, why is what you get out radioactive? And it has to do with this proton and neutron balance. The balance is wrong for what you've made, even though it was right for what you started with. This is a code I wrote in Java. You can actually download it from my website, where I map out all of these different possible combinations of fission. And these are the mass numbers of each of those. And they assume two broad peaks of distribution. This is the smaller fission product, and this is the larger fission product, because each fission generates two of them. Okay? And there's certain numbers of masses that are more common in this reaction than others. You know, like mass number 111, you get it sometimes, but not very often. You know, mass number 93, pretty darn common. That one happens quite a bit. Okay, so you get these two parts, but because they're neutron rich, they have to beta decay a couple of times before they reach a stable nucleus. And let me show you another. Here's a little bit, just a couple of these mass chains. Like let's say you start on 134, you'd go step, step, and you'd be within 41 minutes and 52 minutes, you'd be at a stable nucleus. That one decays really quickly. This one, 12 minutes, 20 hours, 5 days, you're at a stable nucleus. Let's see if any of these guys are anybody that we know. Okay, here's a cesium-137. This one's got a long guy in it, 30 years. Cesium-137 is a little bit of a troublemaker.
Mega years?
Mega years, yeah. Actually, believe it or not, that's not a big deal. And then let me talk a little bit about when you have lots, well, I just got to talk about this when I was over at Mount Royal. Let's talk just somewhat about radioactivity, because I had an erroneous notion of what radioactivity was. I thought that if you had something that had like a half-life of a day, and you had something that had a half-life of 1,000,000 years, it meant that the dude that was radioactive for a day is like for a day and then oh, I'm done. And the dude who's half-life for 1,000,000 years is like for 1,000,000 years and then done. Okay, so you go, well, which one of these is more dangerous? Well, definitely the one that's got a half-life of 1,000,000 years, because that's got to be like radioactive forever, and the dude that's radioactive for a day, that's not a big deal, right? Completely wrong. Okay, utterly backwards. The dude who's radioactive for a day is really, really radioactive. The dude who's radioactive for 1,000,000 years is hardly radioactive at all. Which one of those two is more dangerous? The one that's radioactive for a day, by a long shot. Okay, so your radioactivity is directly and inversely proportional to your half-life. So somebody goes to you, there's something that's got half-life 1,000,000 years. Scary, huh? And you give it to me, I'll put it in my hand. It's not going to hurt me. It's not going to hurt me. There's something that's half-life of a day. You want to hold? No, keep it away from me, man. That stuff is hot, but it's going away fast too, right? So all these guys who have real short half-lives, very, very dangerous. But they're going away real quick. This guy, 2.3 million years, no problem. It's not going to hurt you. It's just not nearly radioactive enough. Another thing I learned about is some of these fission products have a really, really big propensity to eat neutrons. And the way they describe this in nuclear reactions is they call it a cross-section. It's a term that we use to describe how probable is a reaction going to be. Well, one of those fission products is named xenon-135, and here is its cross-section relative to two nuclear fuels. Okay, see these little bitty guys? So imagine we're playing darts or something and throwing them. Which one are we going to hit? When xenon-135 forms from fission, you know, look at all these chains, blah, blah, blah. Where's 135? Ooh. Okay, that's not particularly an uncommon event to form that particular guy. And xenon-135 has a half-life of 9 hours. It's very radioactive, but during that 9 hours, it really wants to eat your neutron. This turns out to be a big problem for real nuclear reactors. It messes up how they want to operate because of the existence of xenon. This actually was a contributing effect to the Chernobyl disaster, was the presence of xenon-135. And it's really hard to deal with in solid fuel reactors. But xenon is a gas. And gases, well, where's my, well, if I open my Diet Coke, what happens to gases in a liquid? They come right out of solution. In a fluid fuel reactor, I'm getting a little ahead of myself, but in a fluid fuel reactor, this troublemaker will come right out of the nuclear fuel and leave the reactor. That is a big, big, big deal. I have a friend I've made online who is a nuclear reactor operator at a reactor in California. And he jokes with me that he got interested in lifter and thorium when I told him about xenon-135. It's like Jerry Maguire. He goes, "You had me at xenon. You had me at xenon." You know. And I said, most people, you know, that's not what we get them at, but that's really kind of cool that you actually, and he goes, no, you don't understand. I'm always fighting xenon in my reactor. That's like all we do as operators is try to deal with this stuff.
In the competition to achieve economic power from nuclear reactors, studies are being conducted on the use of high-performance fuel elements in which some fission products escape into the coolant stream. A large part of the reactor development program at Oak Ridge National Laboratory is directed toward systems in which all fission products are permitted in the circulating fuel stream. These are known as fluid fuel reactors. The molten salt reactor, which is one of these, employs a mixture of molten fluoride salts circulated between reactor and heat exchanger at temperatures in excess of 1200 degrees Fahrenheit. All reactor systems, either the solid or liquid fuel variety with radioactivity in the coolant, cannot be approached for contact maintenance. Consequently, repairs must be made indirectly. The approach in the molten salt reactor system is to have components with long serviceability, so that when they do fail, they can be economically discarded without repairs and replaced in their entirety. The laboratory, as a result, initiated a program to develop an arrangement of reactor components which would permit component maintenance and replacement through remotely controlled operations. This facility is a mock-up of a small reactor system approximately 20 thermal megawatts in size. A simulated fuel mixture of sodium fluoride, zirconium fluoride, and uranium fluoride was circulated through the loop at 1200 degrees Fahrenheit and at 5 pounds per square inch helium blanket pressure. Components include a reactor core vessel which supports a centrifugal sump pump and a 30 horsepower DC motor. The pump impeller circulates 460 gallons of molten salt per minute at 28 feet of head. The motor operates at 1300 revolutions per minute. The reactor is connected to the primary piping circuit by two 6-inch mechanical joints of the freeze flange type. Two heat exchangers of the tube and shell type are arranged in semicircular shape. Each is suspended from a dolly that is free to move laterally during expansion of loop piping and during replacement. Both heat exchangers are connected to the primary and secondary systems by four 3.5-inch freeze flange mechanical joints. Piping for the primary circuits consists of 3.5 and 6-inch standard weight Inconel pipe. Secondary circuits are constructed of 3.5-inch Inconel. In this section, there are special electric heaters which can be maintained remotely for preheating the pipes. Specially designed adjustable spring supports permit all piping to expand or contract freely during operation without overstressing the pipe. The piping and supports were designed to permit removal of the piping and major components from overhead. To remove and replace a component, it must be possible to break and remake pipe connections to extremely leak-tight specifications. Considerable attention, therefore, was given to the design and development of a suitable mechanical joint which would lend itself to remote assembly. The freeze flange developed at the laboratory is used at 20 locations in this system. Such a joint takes advantage of fused salt properties to form a frozen seal of the process material between flange faces. This seal is backed up by a conventional metal O-ring, which seals in the fission gases and also serves as a leak monitor. Flanges are held together by two-sectioned wedge clamps fastened by bolts. A 16th-inch gap exists between the faces. It is in this volume that the salt seal is formed. Pin and funnel guides align the flanges during remote assembly. The mock-up reactor system is operated from panel boards containing instruments which control pipe preheaters, the cooling air to flanges, pump and motor operation, and temperature recorders. The control room also contains controls for the manipulator, overhead crane, and the closed circuit television, all of which are used during remote maintenance. The television system includes two fixed cameras with automatic zoom lens mounted in separate locations in the reactor cell. Two other cameras with three lens turrets are mounted as a stereo pair atop the control room roof. These cameras, located on a dolly which can travel the length of the cell, feed their pictures into a pair of monitors mounted in a stereo viewer. The stereo system is in use more often than the fixed cameras. Signals from all four cameras are fed into the monitors through video switches. To test the maintenance concept, salt was circulated through the system and then dumped before the various reactor components were removed and replaced. In removing the motor, pump, and reactor, the motor is first disconnected electrically by the remote manipulator. Then, three bolts holding the motor and pump spool units together are loosened with a pneumatically operated impact wrench. With the aid of the overhead crane, the motor is lifted from the pump and removed from the cell. The disassembly proceeds with the removal of 6 oil and helium lines connected to the pump. In addition, a speed indicator and 2 thermocouples are disengaged. Once again, the impact wrench is used to free 12 hold-down bolts. The bolts, loosened in sequence, remain in the pump. Four jack bolts are actuated to break loose the seals between the pump rotary and stationary elements. The bolts are turned 1 revolution during each sequence to free and raise the pump evenly. An eye bolt is inserted in the pump shaft to facilitate its removal by the crane. The pump flange O-ring gasket is the final piece of equipment removed in this setup. Total time for removal of the motor and pump was 6 hours. In removing the reactor core vessel, 23 thermocouple and heater leads are first disconnected. After the 4 freeze flange cooling lines are detached, the pump bowl vent is removed. All of these items are left suspended for easy pickup later. on the upper and lower flange clamps are then loosened. The special torque tool consists of two pneumatic air motors ganged to give either alternate or simultaneous operation by air pressure and to absorb counter torque. The same tool, after conversion to a bolt runner, unscrews the bolts until the clamp halves separate far enough to slip over the flanges. One of the air motors simultaneously turns both 2 and 5/8-inch socket extensions through a geared drive. This unscrews both bolts the same number of turns. The loosened flange clamps are moved aside. Then the jack control handles atop heat exchanger dollies are turned to separate the flange faces and to permit lifting of the reactor vessel. The action is alternated between both jack handles after every 2 turns. The reactor remains stationary, while the screw jacks push the reactor piping system, including the heat exchangers, away from the core vessel. This is possible because the entire reactor piping system is floating and free within limits to move in any direction. Approximately 36 counterclockwise turns are needed to open a 2-inch gap between flanges. 4 reactor hold-down bolts are next loosened and left in position. Following attachment of a lifting jig, the reactor vessel is carefully raised from its support stand and removed.